All right, so in the last video, I did the first example of applying algebraic manipulation to help us solve a limit. Let's do another one. This one's a little bit different. It's not as simple as just factoring and canceling common factors. In this example, we have the function 1 over x minus 1/3 divided by x minus 3. So that's like you can call that a compound fraction. It's a fraction with fractions in it. We might just want to simplify it to make it not a compound fraction any longer. And then that might lead us to something which we can actually evaluate. So we're going to, obviously we can't just evaluate this right now because we have, again, division by 0 going on. In fact, we'll have 0 divided by 0, which is called indeterminate. 0 divided by 0 doesn't equal 0, by the way. That is a common misunderstanding. It doesn't equal 0. 0 divided by 0 is an indeterminate form, and it could equal anything depending on the situation. Or it could equal. It's undefined, but when you have a limit that appears that way, it could end up equaling anything. So let's do some manipulation, first with the goal of simplifying this compound fraction. You may remember different strategies for doing this. One is to look for all the denominators and find a common denominator. So in the numerator here we have denominators x and 3. A common denominator would then be 3x. So what I'm going to do is I'm going to multiply the entire numerator by 3x. And of course, if I'm going to do that, I have to also multiply the denominator by 3x. So I'm multiplying by 3x over 3x, multiplying by 1. It's going to keep this equivalent to what we started with. But the benefit of this is when you distribute that multiplication in the numerator. In each case, a factor is going to cancel. So we have 3x divided by x, and the x's will cancel, leaving us with just 3. And then 3x divided by 3, the 3's will cancel, leaving us with just x. Now the fact that it was subtraction is still true. So 3 minus x is what we have in the numerator. In the denominator, we could distribute that multiplication, but I'm not going to. Okay, why would I choose not to distribute that multiplication by 3x? I did it in the numerator, why shouldn't I do it in the denominator? Well, the reason is because actually, now that we have eliminated the compound fraction, right? Now that we don't have fractions within our fraction, this is just a rational function, and what I want to do is try to factor as much as possible and actually find those common factors that will cancel, like in the previous example. You may see it already, right? You may see that we have 3 minus x and x minus 3, which are almost the same, right? They're different from one another because they are opposites. So they differ only in by multiplying by -1. So I can factor out a -1 and get x minus 3 instead of 3 minus x up there. And now I'm ready to cancel that factor, simplifying to -1 over 3x, which is now something which is defined at 3, right? That's defined at 3. So, but it's equivalent to what we started with, except at 3. So I can go ahead and apply my direct substitution and get my limit value of -1/9. So, I hope that was okay. This is probably a fair amount of algebra review. You're probably thinking, wow, I have done this sort of thing before and I never realized why it was going to be useful. But I hope you think that this seems pretty useful. In my opinion, evaluating limits is useful. It would feel even more useful if you knew that we're going to be doing this exact kind of work when we try to figure out derivatives of functions, which are new functions that tell you the instantaneous rate of change of another function. It's essentially the calculus solution to that tangent problem that we talked about earlier. So this is all going somewhere very real world, very applied. Okay, this is all going to be put to use. All right, so the next example I want to do is one that involves some square root functions. So we're going to have the square root of x minus 2 over x minus 4. And again, we have the 0 over 0 type of situation going on. If you attempt to direct substitute, you get 0 over 0. It's called an indeterminate which means we don't really know what's going on. It might be that the limit is undefined, or it might be that it is defined, and we'll just have to find out. What we're going to do here on this one, in order to simplify this, is apply something you've learned before, but maybe in a slightly different way. You may remember rationalizing a denominator back in like early algebra or early arithmetic even, or maybe when you first learned about complex numbers. You encounter this idea a lot, where you want to rationalize a denominator so that your denominator doesn't have any square roots in it. And at the time, your teacher may have just told you that that was a rule, and that felt very unconvincing. I don't really care if I have square roots in my denominator. I'm perfectly comfortable with radicals in my denominator. But this rationalizing idea is super useful in some cases for simplifying things. So in this case, instead of rationalizing the denominator, we're going to rationalize the numerator. And the way to do that is to multiply it by its conjugate. So we have this difference here, square root of x minus 2. The conjugate of that is the square root of x plus 2. It's called a conjugate. And if I'm going to multiply that in the numerator, I'm going to multiply that in the denominator as well. There we go. So that these two things here are called conjugates. And their product is going to be nice and simple, because as you can see, one is a difference and one is a sum. It's like a minus b times a plus b, which when you multiply it out is going to give us a squared minus b squared. It's going to produce that difference of squares, which is kind of the point here. So what we end up with is the square root of x squared minus 2 squared. That is the product you get. Now in the denominator, again, like in the past example, I'm not going to bother multiplying this out, okay? That actually won't be helpful. The conjugates product in the numerator is the key part here that we need. If we don't need to multiply something out, we're not going to, because we'd rather have things factored so that we can find those common factors and cancel them. So aren't you glad we didn't multiply these together? Because check it out. The numerator has simplified to x minus 4, and now the x minus 4 factor is shared in common between the numerator and denominator, so we can cancel it. So that's why I didn't multiply those out. So now that we've canceled those common factors, what's left over in the numerator is going to be 1, and in the denominator I have the square root of x plus 2. Oh my goodness, a square root in the denominator. We'd better rationalize that denominator right away, right? Well, no, please don't do that, because if you rationalize this denominator, you're just going to get back to where we started, which is not as useful. Okay, so in this situation, having that radical in the denominator is much preferable, because this function, while equivalent in most ways to the original one, is actually defined for x equals 4. So we can go ahead and apply our direct substitution, 1 over the square root of 4 plus 2, and we get 1 over 4. And that's it. Limit value is 1/4. I got one more example, but I'm going to put it in another video.